This is one of a series of revision lectures given by the Further Math Support Programme for A-Level Mathematics. In this lecture we're looking at Edexcel Mechanics 1 and the topic is statics of a particle. Now for statics we're looking at forces being in equilibrium. That is that the sum of the forces is in any direction is going to be zero. We're not really looking at Newton's laws. That's in a different topic. So we have the sum of the forces equal to zero. These forces may include frictional forces, and as such you need an understanding, as it says in the specification, of F, the frictional force, being less than or equal to mu r. The maximum that the frictional force can be is equal to mu r, and it will increase depending on the situation so that an object remains in equilibrium, so that the forces sum to zero. Okay, that's really all there is to say about this. You need obviously to be able to resolve forces. That will use simple trigonometry, and to be able to work out the magnitude of resultant forces, possibly using Pythagoras' theorem. We'll now look at a couple of questions which hopefully will illustrate the ideas required. The first question here comes from the January 2010 paper. I'm just reading through first of all. It says a particle of mass m kilograms is attached at C to two light inextensible strings, that's AC and BC, and the other ends of the strings attached to fixed points A and B on a horizontal ceiling. The particle hangs in equilibrium with AC and BC inclined to the horizontal at 30 and 60 degrees respectively, as shown in figure 1. Well, we're told that the tension in AC is a value of 20 newtons, so just adding that into the diagram, we've got 20 along the side AC. The other thing that we know is that the weight is acting at C, so the weight there is a value of the mass m multiplied by g, acceleration due to gravity. There is then another tension that we've been asked to find in the string at acting along CB, so tension T. So that's our diagram complete. Now there are different ways of solving this. I look at two different ways. The first approach is to draw a vector triangle showing these forces. If we do that, we have mg acting downwards, and then at an angle of 60 degrees up from there, we have the force of 20, and then T finishes off the triangle, and T is at right angles to the 20, giving us the 30 degree angle at the top. Just to make clear where that 60 degree came from in the first place, if I add in to my diagram on the right hand side a vertical above C, then the angle that I've drawn in is this one here, which is 60 degrees. Now once you've drawn the vector triangle, this becomes quite a straightforward problem, because we can simply, from our triangle with T marked in there, then we can use the triangle in simple trigonometry to see that tangent of 60 degrees is T over 20. So we can write down from the triangle for part A that tangent of 60 degrees is equal to T divided by 20, and therefore T is equal to 20 tan 60 degrees, and that is 20 root 3 newtons. Using the same triangle, we can find for part B mg, because the cosine this time of 60 degrees, so cosine 60 degrees is equal to 20 over mg, and so m is equal to 20 divided by g cos 60 degrees, and that is equal to, well, cos 60 is 1/2, so that we've got 40 over g newtons, and it's quite acceptable to leave our values in that fashion. Well, an alternative method to that one is to use the original diagram as shown at the right hand side and to resolve the vectors. So first of all, resolving in a horizontal direction, then we can see that t cos 60 is acting to the right, so t cos 60, and then to the left minus 20 cosine 30 is equal to 0. And again, if you solve that, t is equal to 20 multiplied by cos 30. Cos 30 is root 3 over 2. And then dividing by cosine of 60. Cosine of 60 is 1/2. And that again gives 20 root 3. For the second part of the question, resolving vertically, in a vertical direction, we have got 20 sine 30 degrees plus t sine 60 degrees and minus mg equal to 0. So m is equal to 20 sine 30, so that's 20 multiplied by 1/2, plus t sine 60, t is 20 root 3, and sine 60 is root 3 over 2, so we've got 20 root 3 multiplied by root 3 over 2 divided by g. The top line there is 10 plus 30, so 40, so again we get 40 over g newtons. Looking at the marking for that, the marking for the resolution method was done as M1 and then A2 for this first equation here, and an accuracy mark, so giving the 4 in total. You got the accuracy mark once you got the 20 root 3. In the second part of the question, then it was M1 A2 again, and a final accuracy mark at the end. I don't have the actual mark allocation for the other method, although I suspect it obviously 4 marks for each part. I suspect that you would be given 2 of the marks, beg your pardon, 3 of the marks at this stage, and followed by the A1 mark here, and again 3 marks for this and the A1. It's probably worth pointing out that the method of drawing a vector triangle, this method here, is fine with 3 forces. You get a triangle, often right angle, so if it is a right angle triangle, simple trigonometry can be used. It can be used with non-right angle triangles as well, although then you would have to use sine and possibly cosine rules. Obviously, as soon as you get past 3 forces, then resolving vertically and horizontally, or in two directions, is a preferred method. The second question involves a particle being held on a plane by a force P. So just reading through the question, we've got a particle of mass 0.4 kilograms is held on the plane, a rough plane this time, so we've got frictional forces involved, by a horizontal force P newtons. So as the force acts in a vertical plane containing the line of greatest slope of the inclined plane which passes through the particle. This is just basically saying that all the forces are acting in the plane of the paper, as it were. The plane is inclined to the horizontal an angle alpha, where tan alpha is 3/4. Now this idea of giving a tangent of an angle rather than the angle itself is actually quite useful. If we're told that the tangent of the angle is 3/4, then we can draw a little right angle triangle. It's a 3, 4 and of course 5 triangle. If you needed to, you could use Pythagoras' theorem to work out the 5. But immediately then we can see that sine alpha is equal to 3/5 and cosine of alpha is equal to 4/5, 4/5. So that the coefficient of the particle, of friction between the particle and the plane, is 1/3. Given that the particle is on the point of sliding up the plane, find the magnitude of the normal reaction between the particle and the plane, and secondly the value of P. Now the fact that the particle is going up the plane means that the frictional force is going to be acting down, and it's on the point of sliding. So that means that F here is at its maximum value, equal to mu r. The weight of the object is its mass, 0.4 multiplied by g newtons, and then we have a normal reaction which is acting at right angles to the plane. Right, now this question is going to be answered by resolving the forces. However, whereas quite often we would resolve the forces parallel to the plane and perpendicular to the plane, that would lead us to including P in both of our equations. So because P is acting horizontal, a better approach is to resolve things vertically and then horizontally. So first of all, vertically, we could say that there is no component of P, the advantage of doing that, acting vertically. So for the first part of the question, A, I can now write down an equation, alpha, this angle here, so that r cos alpha minus f sine alpha minus 0.4g, those are the forces acting vertically, is equal to 0. Well, now we know that f is mu r, and we know that r is, cos alpha is equal to 4/5 and sine alpha equal to 3/5. So this means that r multiplied by 4/5 minus f, which is 1/3 of r, multiplied by 3/5 is equal to 0.4 G. Now in total then we've got 4/5 and minus 1/5, so 3/5 R is equal to 4/10 G, and that gives R is equal to 2/3 G newtons. Okay, in part B of the question we're going to do a similar thing, this time resolving forces horizontally. So looking at the horizontal forces, P acting from left to right, the component of F, which is F cos alpha, is acting from right to left, so minus F cos alpha. And then also there's the component of R, which is R sine alpha. So those are the three forces which are acting horizontally, or the components of the three forces acting horizontally, and that will be equal to 0. So substituting what we know about that, P minus F is mu times R again, so this is 1/3 R. Cos alpha is 4/5, and then minus R sine alpha. Sine alpha 3/5 is equal to 0. So there we have 4/15, minus 4/15 rather, and then minus 3/5, and 3/5 is 9/15. So in total, minus 13/15 of R. So P is equal to 13/15 R. But we know what R is from the first part of the question, so that's 13/15 multiplied by 2/3 G. Or in other words, P turns out to be 26/45 G newtons. Looking at the allocation of the marks, for the first part, M1A1 for the equation, and once you've got that, a method mark for rearranging and an A mark, accuracy mark, for getting the 2/3 G. There was also in here a B1 mark for the use of F equals mu R. In the second part of the question, the 5 marks came from a method mark for the resolving and 2 A marks at that stage, and then a method mark for rearranging, followed by a final accuracy mark at the end. Okay, that's the end of this revision lecture. Other information and information about other revision lectures can be found on the Further Maths Support Programme website, which is www.furthermaths.org.uk.